Welcome to section 4.4, Arcsine, Arctangent, Arccosine, and Trigonometric equations. At the end of this section, you should be able to answer these four questions. What is interval notation? What do we mean by open and closed intervals? How are the trigonometric arc relations related to the trigonometric inverse functions? Where does the second solution lie in the plane? What are some methods of solution for trigonometric equations? Let's start with a quick review of interval notation. Interval notation is used when we don't want to use the inequality signs to describe a domain of x or a range of y. If we want to express the idea of x being between two values including the endpoints, in other words less than or equal to and greater than or equal to, we use brackets around our endpoints for the interval. For example here, x is between 0 and 4 pi inclusive, uses brackets. If we don't want to include the endpoints, just like x is between 0 and 4 pi without including the endpoints, we'll use open and close parentheses. We can also talk about a half-open interval, which uses one parenthesis and one bracket. As you can see here, x is between 0 and 4 pi, including 4 pi, but not 0, or x is between 0 and 4 pi, including 0, but not 4 pi. First, let's discuss the difference between arc cosine of x and the inverse cosine of x. The arc cosine will mean any of the angles whose cosine is a. So any of these solutions to this particular example would come from the arc cosine, while the inverse cosine would be the value of the angle that satisfies our expression that comes from the principal branch. So this initial value of cosine. The main idea of this section is that for any reference triangle drawn, there is a second reference triangle in a different quadrant that will produce the same value for a given ratio, or trigonometric function. And the determination of this second reference triangle is the basis for the arc functions. So for each arc function, we'll have an initial value from a first quadrant reference triangle, and then we'll have a second value in a different quadrant for each of the different trigonometric functions. Let's take a look at each of them. Let's take a look at the cosine graph. I'm going to draw or place a reference triangle in the first quadrant, which will allow me to get my first solution, or my inverse cosine solution, for an expression involving cosine. Now I have to determine which quadrant will give me an angle or a reference triangle that will produce the same adjacent over hypotenuse situation. And hopefully we can see that this reference triangle here in the fourth quadrant gives us the same adjacent over hypotenuse ratio. So quadrant 1 and quadrant 4 are the two quadrants where the cosine will be the same. The relationship between my first angle, x, and the angle in quadrant 4 would be that they are plus or minus the original angle. So they're opposite pairs. They're a reflection across the horizontal axis. If we want to put that into a formula, here's what it would look like. The arc cosine is plus or minus the inverse cosine, plus any coterminal angles, either 360 degrees or 2 pi, trips around the circle. Let's look at the sine function. Here, if I bring in my original reference triangle with an angle of x, I need to choose a quadrant where the opposite over hypotenuse will produce the same value or ratio for the angle. Well, since the opposite is a positive value, I need to be in the second quadrant to produce the same opposite over hypotenuse ratio. So first and second quadrant angles have to be used for the arc sine. Now, the relationship between my original angle x and my new angle to create the second reference triangle is that they are supplementary, because this is also x. So to achieve my second angle, I would take 180 minus x to find this second angle, theta 2. Or if we're using radians, it would be pi minus the original angle. They're supplementary angles which are a reflection across the vertical axis. The formula here, our arc sine is either the original inverse sine plus trips around the circle, or it's the supplementary angle which we obtain by subtracting the original angle from pi, or 180 degrees, plus those additional coterminal angles. Now let's look at the tangent. Once again, I'll bring in my original reference triangle with an angle of x. Now I have to think about opposite over adjacent for the tangent. Now, here in the first quadrant, that produces a positive value for tangent, since both the adjacent and the opposite have positive values. And the only way I can get a positive value in another quadrant would be as if they were both negative, which places me in the third quadrant. So now I have to find a relationship between my original angle x and my new angle x2. Well, if we take a look, we should recognize that from my first angle, I have to travel 1/2 revolution, or half a circle, to get my second angle. So we're going from quadrant 1 to quadrant 3, and we're going to achieve that by adding half a revolution, either pi radians or 180 degrees. So we have a half revolution difference between the two angles. If we want to look at the formula, we can see that the arctangent is either our original inverse tangent value plus a half a revolution. And that half revolution actually takes into account both situations, the first solution and the second solution in the third quadrant. So here's a recap of our three arc functions: the arc sine, the arc cosine, and the arctangent. Let's start with the arc sine. To solve equations using the arc sine, we first find our initial solution, the inverse sine, and any coterminal angles that apply to the inverse sine. And then we use the supplementary solution, 180 minus the inverse sine, or pi minus the inverse sine, and their coterminal angles to find remaining solutions. The arc cosine uses the inverse cosine plus its coterminal angles, and the negative of the inverse cosine plus its coterminal angles, so that first and fourth quadrant relationship. The arctangent uses the inverse tangent solution, and then achieves all the remaining solutions by using half revolutions, 180 degrees or pi, and adding those to our original solution.